In this video, I want to talk about the order of group elements. And before I start, I'm going to have to review the division algorithm. For the division algorithm, I need to start with two integers, m and n, where n is a positive integer. The division algorithm then says that there exist unique integers q and r, where m is equal to nq plus r, and r is greater than or equal to 0 and strictly less than n. We call q the quotient and r the remainder. As an example, if we do 25 divided by 8, well, the division algorithm wants to know 8 times what? So we know 8 times 3 is 24. One more gets me to 25. So 3 is my quotient and 1 is my remainder. Let's let G be a group and A be an element of this group G. If there is a non-zero integer m such that a to the m power is equal to the identity, then there must be a positive integer n such that a to the n is equal to the identity. So I'm looking for elements that I can raise them to a positive power and get back to the identity. And this is going to be the same as elements I can raise to any integer power and get back to the identity. The order of the element a is the least positive integer such that a to the n is equal to e. And we denote that by vertical bars. We would say the order of a is equal to n. And if there's not a positive integer that gets us back to the identity, if a to the m is never equal to e for any non-zero integer, then we say it has order infinity. Let's look at an example. Let's consider the group S3. Let's find the order of each of these elements. Let's start with 1, 2. If I were to multiply 1, 2 by itself, well, 1 maps to 2, and 2 maps to 1, so 1 maps to 1. 2 maps to 1, and 1 maps to 2, so 2 maps to 2, and 3 stays the same. So the order of this element 1, 2 is going to be equal to 2, since I had to square it to get back to the identity. For 1, 3, 1 maps to 3 and 3 maps to 1, so 1 maps to 1. 2 maps to itself. 3 maps to 1 and 1 maps to 3, so 3 maps to 3. So the order of 1, 3 is also 2. For 2, 3, 1 stays constant. 2 maps to 3 and 3 maps to 2, so 2 maps to 2. 3 maps to 2 and 2 maps to 3, so 3 maps to 3. So once again, I have order 2. Now let's look at 1, 2, 3. If I square this, if I multiply it by itself, 1 maps to 2 and 2 maps to 3, so 1 maps to 3. 3 maps to 1 and 1 maps to 2, so 3 maps to 2. 2 maps to 3 and 3 maps to 1, so 2 maps to 1. If I then multiply that by 1, 2, 3, so essentially cubing my element 1, 2, 3. This time 1 maps to 2 and 2 maps to 1, so 1 maps to 1. 2 maps to 3 and 3 maps to 2, so 2 maps to 2. And 3 maps to 1 and 1 maps to 3, so 3 maps to 3. So this time, in order to get back to the identity, I had to multiply this element by itself 3 times. So the order of the element 1, 2, 3 is 3. Finally, let's look at 1, 3, 2. When I multiply that by itself, 1 maps to 3 and 3 maps to 2, so 1 maps to 2. 2 maps to 1 and 1 maps to 3, so 2 maps to 3. 3 maps to 2 and 2 maps to 1, so 3 maps to 1. If I then multiply by 1, 3, 2 again, 1 maps to 3 and 3 maps to 1, so 1 maps to 1. 2 maps to 1 and 1 maps to 2, so 2 maps to 2. And 3 maps to 2 and 2 maps to 3, so 3 maps to 3. So we have the order of the element 1, 3, 2 is equal to 3 as well. And the order of our identity element would be equal to 1, since we would raise it to the first power to get back to the identity. When our group is multiplicative, and where we're using the group operation of multiplication like I did in my last example, we talk about powers. However, if our group is additive, we need to speak of multiples rather than powers. We would need to be looking at A plus A plus A plus A, etc. So let's do an example with an additive group. Let's consider the group Z6. I want to find the order of each of the elements 2, 3, 4, and 5. Since this is an additive group, I need to add. 2 plus 2 is 4. 4 plus 2 is 6, which is the same thing as 0. So we had 1, 2, 3 2's, which tells me that the order of element 2 is 3. For 3, 3 plus 3 is 6, which is the same thing as 0, which tells me that the order of 3 is 2, since I only had to add it to itself twice. For 4, 4 plus 4 is 8, which is the same thing as 2 mod 6. And 2 plus 4 is the same thing as 0. So I had 3 4's. That tells me that the order of 4 is 3. For 5, 5 plus 5 is 10, which is equivalent to 4 mod 6. 4 plus 5 is 9, which is equivalent to 3 mod 6. 3 plus 5 is 8, which is equivalent to 2 mod 6. 2 plus 5 is 7, which is equivalent to 1 mod 6. And finally, 1 plus 5 is going to be 0. So this time we had 1, 2, 3, 4, 5, 6 5's. So the order of 5 is 6. Let's consider the integers under addition. I want to know the order of any non-zero number. As an example, let's use 2. Since this is additive, we would need to do 2 plus 2 is 4. 4 plus 2 is 6. 6 plus 2 is 8. 8 plus 2 is 10, and we could keep going. But the identity here is 0, and it doesn't matter how many 2's we add together, we would never get 0. And that's true for any integer. No matter how many times you add it to itself, you would never get 0. So the order of 2 in any other non-zero number would be infinite. What's the order of the number 1 in R star and in R? Let's start with R star. R star is a group under multiplication with an identity of 1. So in this case, we're looking for 1 to what power is equal to 1? Well, the order would just be 1, since 1 to the first power is 1. R is just a group under addition. So I would essentially need to know how many 1's I need to add together to get to 0. And that would be never. So in this case, the order of 1 would be infinite.